Welcome. Today we discuss on second unit, which is thermodynamic properties of fluids and their interrelationships. From Chemical and Process Thermodynamic course, I am Dr. Ravi, working as Assistant Professor in the Department of Pharmaceutical Engineering, BVR in Narsapur. Before going to the course content, first we'll see what is the objective of this unit. This objective is to understand, to determine the basic thermodynamic properties of pure fluids and mixtures by using property correlations. The outcome is the student able to understand, to determine the basic thermodynamic properties for pure fluids and mixtures by using property correlation at the end of the unit. So we can see here the mapping between the course outcome and program outcomes. This second unit will contribute to the engineering program outcome. First one is the PO1 is the basic engineering knowledge, and it is also contributes to the problem analysis, 3 out of 3, and PO3 is the design and development of solutions. This unit somewhat contributes to that also, and PO4 is the conduct investigations of complex solutions. So to conduct the complex related problems, this unit also will help you in dealing that. PO5 it is also helps in PO5 for he has given the two that is modern tool usage. PO6 is the engineer and society, the design related problems and society related problems. This unit will also contribute in that. And PO7 is environment sustainability, and next to PO8 is the ethics, and PO9 is the individual and teamwork. And directly it won't give this unit, second unit won't contribute in the PO8, PO9 and PO10. And PO11 is the project management and finance. So how to in the design perspective, how to do as a project manager and finance. And also PO12 is the lifelong learning. So 3 points as given for this. Means this unit will help you to throughout your life this knowledge in your real problems or industrial problems or any social related problems. Now the content of the second unit is PVT, pressure, volume, temperature, behavior of pure substances, equation of state, generalized correlations and eccentric factor, PVT, behavior of mixtures, thermodynamic charts, estimation of thermodynamic properties and relations among them, mathematical relationships among basic properties. Finally, the unit is concluded with the Maxwell relations. First one is the PVT, behavior of pure compounds. Before going into that, actually in industry, if you want to design a fluid passing conducts or fluid passing equipments or fluid storage equipments, you need to know the how the fluid is behaving with increasing of some component, how other properties are changing. Means how we need to know the fluid pressure, volume, temperature, behavioral property before going to design the fluid passage equipments and fluid storage equipment. So the PVT here, the point is here, The PVT behavior is very helpful, especially in designing of fluid handling equipments. So that's the reason here we are going to see the single and mixture compounds, how to determine the PVT behavior, and from there how to determine the other properties. So in that, in the PVT behavior of pure compounds, in that first one is the pressure and temperature behavior of compound. How the single compound is changing or changing with respect to with increasing or with changing the temperature, how the pressure is changing. So here we can see that graph in a pressure versus temperature behavior of a pure compounds graph. In that, y-axis is pressure and x-axis is temperature. So here we can see the line 1 to 2. It is called sublimation curve, and the two so this sublimation curve will separate the solid region to vapor region. So on this line, the solid and vapor both are in equilibrium. Next one is the line 2 to 3. So it is called fusion curve. So this fusion curve will separate the solid region to liquid region. So on this fusion curve, the solid and liquid both are in equilibrium. Next one is the 2 to C. So the line from the 2 to it will extend and terminate at C. So this line is called vaporization curve. So this vaporization curve will separate from liquid region to gas region. So on this curve, the liquid and gas both are in equilibrium. The line 1 to 2 and 2 to 3 and 2 to C. These three lines met one point. This is called triple point. At this point, the solid, liquid and vapor both are in equilibrium. So the temperatures at the triple point are called triple point temperature and triple point pressure. So next one, so after the C is here, it is noted as a critical point. At beyond the critical point, the region is called fluid region. Generally, at a critical point, the liquid region and gas regions are indistinguishable. So that's the reason at constant temperature and decreasing the pressure, in that if that fluid region, if that fluid vaporizing, then we can say that the compound is in a liquid state. Otherwise, at constant pressure, decreasing the temperature, if the compound is condensing, then we can consider that the compound is in a vapor state. So that's why we can distinguish. So here we can see from A to B dashed line is there. This is not a boundary. It says that the liquid region beyond the critical point, when it is not crossing the equilibrium curve, so that phase transition is a very gradual process. rather than, so when the solid region is converting from the solid to liquid region through equilibrium curve, this process is a spontaneous process. Okay, so means any phase is passing through the equilibrium curve to next phase, so that process is a spontaneous process. But apart from that, beyond the critical point, the liquid region, if it is transferring without crossing the equilibrium curve, then the process is a very gradual process. Here we can say that when the phase is liquid region, when the liquid to from the solid to the compound is changing to liquid phase. So at that temperature and pressure is called like a melting point. The compound, the liquid state which is there, initially liquid state, is at what temperature and pressure that liquid state compound is changing into vapor state, that is called a vaporization point. For the vapor compound, at what temperature and pressure it is converting to the solid state, it is called deposition point. Okay, so in other way around, so if the compound, the solid region compound is the solid compound, at what temperature and pressure is converting into vapor region, it is called sublimation point. In other way around, the solid compound is converting into the liquid region, at what temperature and pressure, it is called the condensation point. The liquid in the compound is converting into solid, at what temperature and pressure, that temperature and pressure is called the freezing point. So this is about the changing the temperature, which is changing the temperature, how the pressure of pure compounds are changing for different phases. So this graph explains that. Next one is the PV behavior of pure compounds. Actually, in the PT behavior, in the PT graph, it is not mentioned the what is the change in volume, and the means how the volume is changing, the compound volume is changing. So the PV graph, we can know that what is the change in volume with respect to the other properties. So, and apart from that, in this PV graph, we can see that in the PT diagram, the equilibrium lines are equilibrium curves are like a lines only. But here in a PV diagram, the equilibrium lines are the regions. We can see here we can see here the solid liquid region. So this is the equilibrium line is represented as a region, a solid liquid region, and this is a liquid vapor region, and this is the solid vapor region, and this is a vapor. This is the fluid region. Beyond the critical point, this is a liquid region, and this is a solid. So here we can see that with changing that, we can see that means how the volume is changing of a particular compound. So if you can see in this next graph, so this is a TC is the critical point, and the T1 is the less than the critical point at critical temperature, less than the critical temperature. That is that we are represent here. It is represented as T1. When at that particular temperature, that is the T1. So when the volume is reducing, the pressure is increasing. The pressure is increasing in the vapor region. After reaching the liquid vapor region, even though the volume is decreasing, there is no change in the pressure in the liquid vapor region. Later, when it is reached to the liquid region, when the volume is decreasing, the pressure increases spontaneously in a liquid region. That we can see at a particular temperature. If the different temperature, the trend is looks like same only, but a lower pressure. So at critical point we can see that at critical temperature, with the decreasing the volume, the pressure is increasing, and it reaches to the critical point. After that, spontaneously, when the volume is decreasing, spontaneously pressure is increasing. So this graph shows at a particular temperature, or with increasing the temperature, how the volume is when the volume is changing, when the volume is decreasing or volume is changing, how the pressure is changing. That can be seen from this image. Next one is the equation of state. The equation of state is a mathematical expression in terms of pressure, volume, and temperature. So if you of a pure compound, using this this equation of state, we can easily determine the unknown thermodynamic properties. For example, if we know the any two thermodynamic properties, from there we can easily calculate the other thermodynamic properties using the equation of state. Generally, there are various many types of equation of states are there, each one suitable for different types of a substance and conditions. So here we discuss a few equation of states. That is, first one is the ideal gas law, virial equation of state, cubic equation of state, and again the cubic equation of state is based on the complexity, classified again van der Waals equation of state, Redlich-Ong equation of state, and Feng-Robinson equation of state. So these are the mathematical expression in terms of pressure, volume, and temperature. From that, from this equation of state, we can determine the thermodynamic properties. First, we will see the ideal gas law. The ideal gas law is the simplest equation of state. So it assumes that it name suggests like that. It assumes that the gas is in a the gas behave as a ideal gas. Means the gas particles they don't have a volume, means volume is zero. There are no interaction between those particles. This expression, the ideal gas law expression, is developed based on these two assumptions. So the ideal gas law expression is PV is equal to nRT. Here P is equal to pressure, V is equal to volume, N is equal to number of moles, R is equal to gas constant, and T is the temperature. Next one, virial equation of state. The virial equation of state is deviated from the ideal gas law. Means in ideal gas law, it is assumed that the gas particles volume is zero. There are no interactions. But here in a virial equation of state, it is the expression is developed based on the gas particles. It has volume, and there are attractive interaction between those particles. Okay, so using this virial equation of state, we can determine the phase transition and compressibility factor and heat capacity. So the virial equation of state expression is PV is equal to RT into 1 plus B by V plus C by V square plus D by V square, so on. Here the second term, it is called second virial coefficient. Third term, it is called like C by V square is called third virial coefficient. Fourth term, it is called fourth virial coefficient. The second term, the second virial coefficient, it corrects for the excluded volume of gas particles. Means means this term it will contribute the gas particles having a particular volume. And the third term describes the two body interactions. Means the two particles are there, the interaction between these two gas particles is contributed by the third virial coefficient. Fourth virial coefficient, three body interaction, means 1, 2, 3 particles are there. The three particles are hitting together, means interacting at a time 3 particles. So that is contributed by the fourth virial coefficient. Like fifth virial coefficient, next to 4 body interaction. Generally in a state the 4 body interaction, 5 body interaction, there are very few, and so that they contribute to the expression very less. So we can see that, for example, let's say second virial coefficient B by V, assume that V is equal to 0, and third virial coefficient, and from the third virial to so on, no interactions between the particles. Then these all the terms is 0, and this is 0. Finally, this is PV is equal to RT, means it is ideal gas law. Means it is deviating from the ideal gas law by introducing the second virial coefficient, third virial coefficient, so on. Next one is the cubic equation of state. The cubic equation of state are widely used in the pharmaceutical engineering, chemical engineering, and process simulation. Actually, the cubic, based on the term, and so the expression, the equation of state name came, means in this expression the volume is having 3 means cube. So that's the reason these expression, these equation of states are called cubic equation of state. Here these cubic equation of states are complex in nature, so that they are useful to determine the thermodynamic properties inaccurately. And they are very suitable for the real gas systems. The general expression for cubic equation of state is P is equal to RT by V minus B minus A by V square plus 2BV minus B square. So we can see that P is the pressure, V is volume, R is gas constant, T is temperature. A and B parameters specific to the substance, known as van der Waals coefficients. In this expression, the first term contributes the volume. The gas particles are having the volume, and this is not excluding the volume. So the second term in RHS corrects the alternate attractive forces between the gas molecules. Generally, there are the general cubic equation of state can be modified based on the requirement. Based on the how much complexity and accuracy you want, based on that the general cubic equation of state is modified. In that, the van der Waals equation of state and Redlich-Ong equation of state, Peng-Robinson equation of states are here we are going to discuss them. In that, the van der Waals equation of state is the simplest equation of state in the cubic equation of state. It provides a better approximation for real gases, and it can be validated for moderate pressure and temperature. The expression for the van der Waals equation of state is P is equal to RT by V minus B minus A by V square. The earlier it is mentioned, the first term in the right hand side, it contributes the volume, including the gas particles volume, and second term accounts for the interaction between the particles. Here, the A and B are the van der Waals coefficients. The A and B are determined from the critical temperature, critical pressure, and isentropic factor. So here A is equal to 27 by 64 into RTC whole square by PC. The B is equal to 1 by 8 into RTC by PC. So next, Redlich-Ong equation of state. The Redlich-Ong equation of state is another cubic equation of state. It is commonly used to describe the behavior of real gases. It includes both attractive forces and repulsive forces. It provides a more accurate description for real gas behavior compared to the ideal gas, particularly at moderate pressure and temperature. The expression for the Redlich-Ong equation of state is P is equal to RT by V minus B minus A by under root T into V plus B. Here of course the P is the pressure, V is the volume, R is equal to gas constant, T is temperature, and A and B are the parameter specific to some substance. These are the parameters specific to the substance. So the A and B are determined from the expression. A is equal to 0.42748 RTC whole square by PC. B is equal to 0.08664 RTC by PC. So this is the Redlich-Ong equation of state. Next one is the Peng-Robinson equation of state. So the Peng-Robinson equation of state is useful to determine the basic thermodynamic properties of pure gases and liquids also. The expression for this is equal to P is equal to RT by V minus B minus A of T, V into V plus B into V minus B. So these A and B are the parameters, especially depends on the function of temperature. So here the A and B can be determined in that A of T is equal to 0.45724 into RTC whole square by PC into alpha T. So alpha T is also can be determined from 1 plus K into 1 minus under root T by TC whole square. So here the K is equal to 0.37464 plus 1.454 omega minus 0.26992 omega square. And this from here, from the eccentric factor, after knowing the eccentric factor, we can substitute in alpha T. After knowing the alpha T, we can determine the A of T. So B can be determined from 0.0078 RTC by PC. So in this way, these cubic equation of states are useful to determine the real gas thermodynamic properties in a more accurately manner at moderate temperatures and pressures. Next one is the eccentric factor. The eccentric factor is introduced by K.S. Fitzgerald. So the eccentric factor, it explains about how much the real gas is deviating from the ideal gas based on the value. So generally, this eccentric factor is determined from the experimental data. Generally, this eccentric factor varies from 1 to -1. When the eccentric factor value is very near to the 1, means the fluids are behaving approximately ideal gases. When the eccentric factor value is deviating from the 1 too far, then the fluids the gases are deviating from the that much from ideal gases. So before the eccentric factor was found, and there is one statement that is called two-parameter theory of corresponding states. It says that all the fluids which are having the same reduced temperature. Reduced temperature is equal to T by Tc. T is the operating temperature, Tc is the critical temperature. All the fluids which are having the same reduced temperature and reduced pressure, they are approximately having the same compressibility factor, and they are all deviating same amount or same degree of deviation is there for those fluids. Means, so the fluids which are having the means they said all the fluids which are having the reduced pressure and reduced temperature having the same compressibility factor and same amount, same degree they are deviating from the ideal gases. But later it was found that it is only true for the simple compounds like argon, krypton, xenon, but it is not true for the complex fluids. So later the another factor is introduced, that is the eccentric factor. The eccentric factor. The eccentric factor says that all the fluids which are having the same eccentric factor and same reduced temperature and reduced pressure, this same eccentric factor, reduced temperature and reduced pressure, these are all compounds having the same compressible factor and the same degree they deviate from the ideal gases. So this is later it was found that it is true for the true in a later in a circumstances. So this thing the statement is called the 3-parameter theory of corresponding states. Because in the 2-parameter theory of corresponding state, there are two parameters has taken, like a reduced temperature and reduced pressure. The fluids which are having the same reduced temperature and pressure, they are having say compressible factor, and along with that the fluids same degree they deviate from the ideal gas. That is it, because 2 parameters are considered. Here the 3 parameters are considered. This it is called 3-parameter theory of corresponding states. In that 3 parameters are the reduced temperature, reduced pressure, and eccentric factor. The eccentric factor. Whenever these 3 are equal to the fluids, then the compressible factor is same, and they same amount they deviate from the ideal gases. Next one is the generalized correlations for the gases. So the generalized correlations are the mathematical expressions. They are useful for to determine the basic thermodynamic properties whenever the data is missing. For example, in case of you want to design any equipment, if you need exact data, but approximate data it is sufficient for your calculation. Then these generalized correlations are useful to determine the thermodynamic properties. So in that the commonly used generalized correlations are the equation of state. Up to now we have seen the equation of states. So there are in terms of pressure, volume, and temperature. The Pitzer correlation for compressibility factor. From using this general correlation, the compressibility factor is calculated. The Lee Kessler generalized compressibility chart are also useful to determine the Z compressibility factor. Lee Kessler generalized enthalpy departure chart is useful to estimate the enthalpy. And the transport property correlations, another generalized correlation is useful to estimate the viscosity thermal diffusivity and thermal conductivity. So these are the few so many generalized correlations are there here. Here it is mentioned it is mentioned few. So in that we have already seen the equation of states also generalized correlations. We can, using them we can determine the thermodynamic properties in terms of pressure, volume and temperature. Now we will see the Fitzgerald correlation for compressibility factor. So the expression is Z is equal to Z0 plus omega into Z1. Here is the Z0 and Z1 are the functions of reduced temperature and reduced pressure. So for simple fluids like argon, krypton, xenon, the omega eccentric factor is 0. So then what will happen? The Z is equal to Z0. So the Z0 is a function of reduced temperature and reduced pressure. Thus, actually the second term is only small correction for above equation, because so it won't give the it won't give strong errors if you neglect that second term. So this Fitzgerald correlation for compressibility factor, by using this we can determine the compressibility factor. From the if we know the compressibility factor from this correlation, then we can determine the if you know the critical temperature of that compound, we can know the what is the operating temperature. If you know the operating temperature, we can know the critical temperature, because reduced temperature is equal to the T by Tc, means the operating temperature by critical temperature. From that we can know the when you know the temperature and pressure, from there we can know the other properties. Like that, this generalized correlation is helpful to determine the thermodynamic properties. Next one is the PVT behavior of mixtures. So up to now we have seen the pressure, volume and the temperature behavior of the single compound. Now we will see the mixtures. Actually the PVT behavior of mixture is also very important concept, because to determine the phase equilibrium, reaction kinetic and separation process. Next one, PVT behavior of mixtures. Generally up to now we have seen the PVT behavior of single compound. Now we will see the PVT behavior of mixtures. Means mixtures, how to determine the from the correlations, how to determine the basic thermodynamic properties of mixtures by using the correlations. So because it is also very important determining the mixtures thermodynamic properties, especially to determine the phase equilibrium, reaction kinetics and separation process. If the mixtures are ideal mixtures, then the PVT behavior is given by the Dalton's law. From there, if the mixture is considered as a non-ideal mixture, then the Sauvy-Redlich-Kong equation is helpful to determine the basic thermodynamic properties for non-ideal mixtures. And in that next Peng-Robinson equation also another expression is useful to determine the basic thermodynamic properties of the mixtures of non-ideal. So here for ideal mixtures, the ideal mixtures PVT behavior is explained by the Dalton's law. In that, the Dalton's law states that the total pressure exerted by a mixture is equal to the sum of the partial pressure of each component of gas. So means that the mixture, the total pressure is equal to the individual pressures of the constituent which are there in the mixture. That is equal to, the expression is like this. P total is equal to P1 plus P2 plus so on Pn. Here the P total is the total pressure of the mixture, and P1 comma P2 comma so on Pn are the partial pressure of each component. Next one is the non-ideal mixtures. The Sauvy-Redlich-Kwong equation is helpful to determine the non-ideal mixtures basic thermodynamic properties. We have seen already this expression, that is P is equal to RT by V minus B minus A by under root T into V plus B. So this we have already seen. And next one is the another expression for non-ideal mixtures, Peng-Robinson equation. So this is also we have already seen. Next one is the thermodynamic properties and relations among them. So now first we will see the basic thermodynamic properties. So fundamental thermodynamic properties. So later after that we will see the what is the how to develop the correlation between these fundamental properties. So first one is the internal energy. So internal energy is stored energy within the system due to the motion and interactions of its constituent particles. So for internal energy, the expression is U is the internal energy is equal to W plus Q. Here W is the work, Q is the amount of heat. So next another fundamental property is the enthalpy. Enthalpy is a measure of the total heat content which is there in the system. Total in the internal energy is the energy stored within the system. This is the because of the molecular motions, vibration, translation motion, vibrational motion. The enthalpy is the total heat contained while the system is changing one phase to another phase, or when the system is in a process. So this enthalpy is denoted with H, that is equal to U plus PV. Next one is the Helmholtz free energy. So Helmholtz free energy is helpful to determine what is the maximum available work is there in the system. Okay, so here in other words, it represents the energy available to do non-mechanical works like chemical reactions, phase transitions, while holding temperature and volume constant. So the Helmholtz free energy, it says what is the free energy, or what is the energies available to do non-mechanical work. So the formula, it is this Helmholtz free energy is represented as A is equal to U minus Ts. So next one is the Gibbs free energy. The Gibbs free energy is also same, means what is the available work is there in the system at a constant temperature and here pressure. In the Helmholtz free energy is the maximum useful work that can be extracted from the system at constant temperature and volume. This Gibbs free energy is a constant temperature and pressure. Okay, so it is represented as G is equal to H minus Ts. So these are the thermodynamics fundamental properties: internal energy, enthalpy, entropy, Helmholtz free energy, and Gibbs free energy. So now property correlations. First we will see in terms of internal energy. So we already know that internal energy U is equal to W plus Q. For n moles, when we can write the NU is equal to W plus Q, because this W is the work, this is the heat. We cannot apply the number of moles to that. Okay, now the differential change, if the small change in the internal energy, then we can write we can write d of Nu is equal to dW plus dQ. Okay, for reversible process we can write d of Nu is equal to dW reversible plus dQ reversible. Okay, but we already know dW reversible is equal to we already know P into V2 minus V1. We have already seen how to determine the work in a thermodynamics point of view. V2 minus V1. We can write this one as a P into V1 minus V2 in terms of minus is coming. So this we can write dW reversible is equal to minus P into d of NV. Okay, so that this is the expression for that. Next one, we already know ds is equal to entropy is equal to dQ reversible by T. So from here we can write dQ reversible is equal to T into, from here we can write dQ reversible is equal to ds into T, T into d of Ns. So now you substitute them in a d of Nu equation. So we can get that minus P into d of Nv plus T into d of Ns. So this is the property relations. Next one is the enthalpy. Same. So enthalpy, we know the formula H is equal to U plus PV. So for n number of moles, then we can write as a NH is equal to Nu plus P into NV. So apply the both sides derivation, because means for a small little change, if you want to know that what is the little change in enthalpy, apply the derivation both sides. So then we will get the d of NH is equal to d of Nu plus d of P into Nv. Okay, so so now d of N H is equal to d of Nu plus, this is actually both are the parameters. So that's the reason we need to derive both terms. So derivation of the both terms is first term into second term derivative, d of Nv plus second term into, that is Nv, first term derivative, the dP. Okay, substitute the du. What is the du formula? So d of Nh is equal to, du is a minus P into d of Nv plus T into d of Ns. Okay, plus P into d of Nv plus Nv into d into P. So here both are get cancelled. Finally we will get the d of Nh is equal to T into d of Ns plus Nv into dP. So this is the property relation. So in the same manner, Helmholtz free energy, we know Helmholtz free energy A is equal to U minus Ts. Okay, for n moles, Na is equal to Nu minus T into Ns. Same, apply the for small differential change, that is d of Na is equal to d of Nu minus d of T into Ns. So in the same manner here also, d of Na is equal to d of Nu minus Now minus d of t into ns. So when you derive this, d of n a is equal to d of nu minus first term into second term derivative d of ns, again minus second term into first term derivative dt. Okay, again substitute this one, d of n a is equal to minus p d of nv plus t d of ns minus t into d of ns minus ns into dt. So here, so this one and this one get cancelled. D of n a is equal to minus p into d of n nv minus ns into dt. So that is the final expression. We got this. Next one is the Gibbs free energy. So we know the Gibbs free energy formula, G is equal to H minus Ts. Now for n moles, now Ng is equal to G is equal to H minus Ts. Now for number of moles, n moles, Ng is equal to N H minus T into Ns. Okay, so for differential change, means very small change, apply the derivation both sides. D of n g is equal to d of n h minus d of t into n s. Okay, so now d of n g is equal to d of n h minus first term into second term derivative d of n s minus second term into first term derivative dt. Now substitute the nh, d of nh, the formula. So d of n g is equal to nh formula is t into d of n s plus n v into dp. So minus t into d of n s minus n s into dt. So t into both are, this one plus and minus both are get cancelled. Finally you will get the d of n g is equal to n v into dp minus n s into dt. Okay, so these are property relations among them. So we can write like all together like a d of nu is equal to minus p into d nv plus t into d of ns, whatever the property relation we got. Now write together, and from there apply for 1 mole of a homogeneous fluid at a constant composition. So then the n is here the apply n is equal to 1, then we will get the du is equal to minus p into dv plus t into ds, dh is equal to t into ds plus v into dp. Next dA is equal to minus p into dv minus s into dt. dg is equal to v into dp minus s into dt. So these are basic thermodynamic properties and relations among them. Next one is the Maxwell equations. So we can develop the set of equations by applying criteria of exactness for differential expressions. Means we can write these fundamental properties in other forms also. So this means in a criteria from using the criteria of exactness. So these expressions are called Maxwell's equations or expressions. So in that, first assume the f and property is there, that is f, that is in terms of x comma y. So that is f is equal to function of x comma y. Now apply the total differentiation, that is the total differentiation df is equal to total differentiation df is equal to dou of f by dou x at constant y dx. This is the total differentiation plus dou f by dou y at constant x dy. So this is the total differentiation is defined. So assume like m is equal to, here assume m is equal to dou f by dou x at constant y, and n is equal to dou f by dou y at constant x. So we can write this one as the df is equal to m into dx plus n into dy. Okay, we can write like that. So now we have a m is equal to now m is equal to dou f by dou x at constant y, and n is equal to dou f by dou y at constant x. Now again do the derivation. So for here dou m by dou y, so that is dou square f by both side, do the derivation both side, dou square f by dou x dou y, dou n by, again this is dou x dou f by dou x dou y. So both are same, means dou m by dou y is equal to dou n by dou x. Okay, we can write like this because both are equal. So finally we can write df is equal to m into dx, the expression m into dx plus n into dy into in terms of dou m by dou y at constant x, dou n by dou x as constant y, that we can write. So in the same way, we already know du is equal, means m is there and in terms of y. Okay, so n in terms of x. Okay, we can see same. So this is a df is like, it is same like a m into dx plus n into dy. So dou t by dou v at constant v. Next to dou t by dou v and dou p by dou s as constant v. Okay, in the same way, dou t by dou p, dou v by dou s at constant entropy and constant pressure, and this is dou p by dou t at constant v, dou s by dou v at constant t. So here the dou v by dou t at constant p, dou s by dou p at constant t. So we will get the minus here. So these are called Maxwell expression. So with this we completed the unit 2. So here we learn the determine the fundamental thermodynamic properties of pure and mixture fluids by using the property correlations. So with this we completed. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.